quantum measurements, and quantum information theory. So Professor Ushadevi, over to you, and we are eagerly looking forward to hear you. Could you work with your video? Could your video be turned on?
Check. Anyway.
It's fine if it doesn't, but
yeah, it is okay. It was not working. Now I have to try that. I think it's okay. I will try to switch it on. I have already gone into a full screen mode, so I have to go back and try working on my video.
No, it's okay.
Let me.
Please let that be. I will hand over the platform to you.
Yeah, please. Thank you.
And I will request the audience to raise their hands if they have questions. We could, of course, take it along the way if the speaker thinks that's okay. Otherwise, we will take questions in a sequential manner at the end of the talk. What would you prefer, Professor?
It is fine for me. Anytime if they raise questions, it will be good. I will be able to interact with them. That's good.
Okay, I'll keep track. Thank you.
Over to you, please. So I hope the screen is visible and I am audible.
Yes, both.
So, fine. So I was told to address students who are physics undergraduates, graduates, and it's a kind of heterogeneous crowd. So I planned it in some specific mode, which I hope I will be able to convey in 1 hour's time. So let me thank the organizers for giving me this opportunity to talk to this audience. So I am going to talk about the role of geometric visualization, not to the extent of applications, but it is the kind of mathematical unraveling of geometry of quantum states that we encounter. So this is these are some of the pictures that I will be talking about. A basic Bloch sphere and then Majorana representation of pure symmetric states and the steering ellipsoid picture and how they have kind of mathematical analysis and analytical results lead to the clear identification. So these are the papers that our papers, which I am going to kind of consolidate with in a manner in which it reaches you. So now we all know that Bloch sphere picture of qubit is very valuable, and we kind of take it for granted that we can write a Bloch sphere and put a point and work out what is the dynamics in terms of only Bloch sphere, but not with a quantum state. So that is kind of we are used to. So now what is a generalization of such a Bloch sphere picture is not very clear. So do we have such a picture? Has been attempted by many people. So I am going to talk only about where it is kind of neat, elegant, and easy for our understanding, hopefully. So one is the Majorana stellar representation, which is only allowed for pure permutation symmetric N-qubit states. That is a representation of spin n/2 states as n points on the Bloch sphere, which Majorana had perceived in 1932, which was not noticed that time, but in quantum information theory, people are paying attention to Majorana stellar representation. And the other one is the geometric picture associated with stochastic local operations and classical communications on qubits, which leads to some structure of geometry. That is what kind of a geometric picture it gives and what kind of information it carries, which wouldn't have been noticed if we had only stuck to quantum state description and some kind of computation. That may be a higher claim. But I just want to mention that Plato, in his academy, there was this board: let no one ignorant of geometry enter here. I don't claim such grand status for this my talk here, I would just say, I would make the geometry that I have learned by working on this particular research. I'll make it kind of clearer as we go ahead and explore. So now what we have as the outline is qubit and Bloch sphere. That is well known. It is just to warm you up. And then we have N-qubit permutation symmetric pure states. How do we represent, how we are able to write them as N stars on the Bloch sphere. And then the two-qubit states and ellipsoids inscribed within the Bloch sphere. That is, by restricting ourselves to Bloch sphere, what visualization can we go ahead? That's what we want to talk about. A pure state of a qubit, we know it is represented in terms of the standard qubit basis. So now these two parameters characterize a qubit pure state. And then we all know that the density matrix of a qubit for a pure state, it is given by, that is the state that we wrote here. Pure density matrix is a projector, and it is given, if I express it in terms of a matrix basis, that is Pauli matrix basis, I will realize that it is a density matrix is a vector in matrix space, and it can be expanded using orthogonal basis, which is given by the Pauli matrix. And then once I take the state parameters, density matrix expanded in terms of the Pauli matrix basis, I do notice that the S1, S2, S3, the parameters, they turn out to be a unit vector. And I do have a star picture for a qubit. Any pure state of a qubit can be written as a star on the Bloch sphere. So now, so that will relieve me from my usual quantum state if I want to continue only with such a picture and do dynamics. But then we move ahead and look at what are general properties of a density operator. It's Hermitian, it is unit trace, and it's positive. And in D dimensions, a pure state has 2D minus 2 real parameters. And for a pure single qubit state, that is D is equal to 2, I do only have 2 real parameters. That's which led us to the Bloch sphere, point on the Bloch sphere. Now we will have to go ahead with mixed state density operator. Then we do have a Hermitian matrix with trace 1 has D squared minus 1 real parameters. So we do realize that mixed qubit state has D squared minus 1, 3 real parameters. In such a case, this S1, S2, S3 do not correspond to a unit vector, but it would correspond to a vector with normalization less than 1. So we do have representation of mixed states as points inside the Bloch sphere. So now, when we go ahead to a 2-qubit density matrix, it is just to, because I will be using this, I will just say that we have an orthogonal matrix basis constructed from Pauli matrices. We take sigma mu, tensor sigma nu, and it is an orthonormal basis. And we expand a 2-qubit density matrix in terms of parameters given here. As we know, we have 15 real parameters because D is 4. 4 squared minus 1 is 15 real parameters. So we represent this in terms of a matrix here. So because density matrix is Hermitian, the matrix lambda mu nu, that is indices mu nu, if I write it as a matrix, it is a real matrix, but not symmetric, not Hermitian. It is a real matrix. That's all. No other properties for it. So if I write the 4x4 real matrix, this has a form given in this particular way, where R is the Bloch vector of the single qubit. There are 2 qubits. One of the qubits has Bloch vector R1, R2, R3. Another qubit has S1, S2, S3. And then I have a correlation matrix T, which is real. So we have R, S3. Yes, please.
Why does this matrix have to be real?
All right. Take rho AB and let us take a Hermitian conjugate, rho AB dagger. So where will it will go on sigma mu dagger and sigma nu dagger, okay? And lambda mu nu star. it will be there. And sigma mu dagger is sigma mu dagger is sigma mu. So I will get rho AB dagger is equal to rho AB implies that lambda mu nu star is equal to lambda mu. It's a simple hermiticity condition which tells me that lambda is a real matrix. No other properties, special properties.
Thanks. That's okay. Yeah, that's very simple.
Yeah. So now this matrix plays a big role in the geometry. So I am talking about it. And now you have S 3 parameters, R 3 parameters, and T matrix has 9 parameters. It's a real 3x3 matrix. So total number of parameters is 15, and a density matrix can be mapped to a real matrix form like this. Just that it is real. That's all. So now if I have to take, so I just again repeat it, there are 15 real parameters. Now I move ahead to a permutation symmetric 2-qubit state, because I'm going to talk about Majorana representation, where we are only restricting to permutation symmetric states. If you take a permutation symmetric 2-qubit state, it is C2, tensor C2, complex two-dimensional space, but symmetrized. So this is a three-dimensional subspace of the 2-qubit full space. So now when we symmetrize, we do get only 2-qubit, that is three-dimensional subspace. And this is spanned by the eigenstates of angular momentum, that is 2 spin halves add to give you a spin 1 and spin 0. Symmetric states belong to a spin 1 sector. So there are 3 states, and any density operator which is only restricted to this space is a symmetric operator, density matrix. And symmetric 2-qubit density matrices, even though they are 4x4, we can find a transformation where they will go to a 3x3 form, that is the Clebsch-Gordon transformation. So we have such a feature. But what is permutation symmetry in terms of the parameters? That is, we have been talking about states and their parameters. In general, 2-qubit density matrix has 15 real parameters. But when it comes to permutation symmetric states, we do notice that state parameters will get reduced to 8. How do I count it? I can count it in 2 different ways. One is I am restricted to a 3-dimensional subspace, and density matrix in 3-dimensional subspace has 3 squared minus 1, 9 minus 1, 8 parameters. But if you look at a 2-qubit density matrix, and I want to look at what is a symmetric density matrix, I will notice that 2 qubits inside a symmetric state should be permutation symmetric. That is, if I take a single qubit, 1 qubit picked from a symmetric state, it has a S as its Bloch vector, R as the Bloch vector for the other one. S should be equal to R for a permutation symmetric 2-qubit state. And also the T matrix should be symmetric. In a general 2-qubit system, T is not symmetric, it's only real, but T is equal to T transpose in a permutation symmetric state. In addition, I have a condition that trace T is equal to 1. What is the origin of that? That comes from 2 spin halves will add to give you a spin 1. There I have a J squared is equal to J into J plus 1 condition, which is hidden in T11 plus T22 plus T33 is equal to 1, which can be worked out. I won't say that. So there are 3 parameters here, and T is equal to T transpose means 6 parameters with trace T is equal to 1, 6. Sorry, 5 parameters plus 3 parameters, there will be 8 parameters. S and 5 parameters of a real symmetric correlation. With that, we can generally write a 4x4 form of a pure 2-qubit density matrix, not pure. So if I write it, diagonal elements of a density matrix are real, and trace rho is equal to 1 means I have this condition. So I have 1 plus 1, 2 real parameters, D ignored because A plus D plus 2C is equal to 1. And there is E complex 2, 2 plus 2, E and B, 2 plus 2, 4. 4 plus A is 1, C is 1. And then there is a F here. So together I have 8 parameters. It is written specifically to show that there are 8 parameters. But which parameterization works for me to have a visualization is a different story. It is to show that it has, whichever form you take, it has to have same structure. Now I move on to pure symmetric n-qubit states. That is to say, what Majorana had proposed in his 1932 paper, it was to say, if you take a pure spin J quantum state constituted from n spin half particles, if you add n spin halves, maximum value of angular momentum is n by 2. If you take such a spin n by 2 quantum state, I will give a representation is what Majorana tells you. What does he do? He says symmetric psi is nothing but I take qubits. Qubit state is given by this, which we have seen. Any qubit, pure state of a qubit is written like this. Majorana calls it as constituent spinors. Take a state like this and you put them in order and symmetrize them so that the state is permutation symmetric. Under interchange of two particles, it will remain the same. So pick any n such states and symmetrize it. You get a state which is a spin J state, is what Majorana will tell you. Here, P corresponds to n factorial permutations. That is, if I have 1, 2, 3, then I have 2, 3, 1, 3, 2, 1. All kind of permutations should be taken care of, and a normalization factor appears here. If you do that, he would say, Majorana would say, why Majorana was interested in it? He was very much, he appreciated the qubit Bloch sphere picture and the magnetic precision picture. When you apply a qubit in a magnetic field, the Zeeman precision of the qubit vector on the Bloch sphere inside him. So he wanted to check what is it possible to generalize it. So this is very useful today in quantum information theory. So this geometry, what kind of geometry it has? So I have n qubits and I permute them. I get a n qubit state, which is permutation symmetric. Now what should I do? I will now take, let us only restrict to a spin J state, and the dimension of the spin J state is 2J plus 1. There is an error here. 2J plus 1 is equal to, J is n by 2. 2J plus 1 is equal to n plus 1. It is a n plus 1 dimensional subspace of 2 to the n dimensional Hilbert space. When I am, this is also a superscript, C2 to the power n, that is 2 to the power n dimensional Hilbert space. And then I have a symmetric subspace, which is 2J plus 1 or n plus 1 dimensional subspace. So there, what are our basis vectors? They are our Jm states. That is, J is n by 2 and m is k minus n by 2 is what we write. And we can write such the key states or whatever are Jm states in terms of the qubits as permutation symmetric. I have all permutations. If I write k value to be, say, 1, then I have one number of 0 and all others are 1. So this can be constructed. That is, I can write a spin J state in terms of the constituent qubits or constituent spinors. Now I count. So if I take an arbitrary spin J state, I can expand that state in terms of coefficient Ck in this basis. That is a usual vector expansion. In a quantum state, I have Ck determining my n pure state here. Now, what is the Ck? How many numbers are there? Again, counting. So if you take Ck, there are actually n plus 1. That is, dimension of the Hilbert space is n plus 1. It's a n plus 1 componental column. So you have n plus 1 complex number, Ck. So if you take one overall phase and one overall normalization, that will make it n plus 1 into 2, that is 2 real numbers. So 2 times n plus 1 minus 1 overall phase minus 1 normalization constant, we get 2n real parameters for a pure symmetric n qubit state. So now we notice that these 2n parameters agree perfectly with the alpha L, beta L parameters of the constituent spinors. That is, I am taking n spinors and permuting them to create a permutation symmetric state. If I write it in the n spin J state format, I have 2n parameters Ck, and I have 2n parameters from the Majorana way of symmetrizing n distinct spinors. So how is there a relation between the two? That's what gives us the geometry. So now I notice that I don't explain how I get it, but this is what is called as a Majorana polynomial equation, and that involves the coefficient Ck of this particular representation. That is, spin J state can be expanded in terms of Jm basis, and there are 2n parameters in these complex Ck's. So that is the Ck, and I have a z to the power k, where z is tan beta L by 2 e to the I alpha L. What is that? That is the representation for the spinors. E epsilon here consists of a beta L alpha L. That is, a orientation on the Bloch sphere is of a qubit is decided by alpha L beta L, and a n distinct n qubit state which is symmetric, it has 2n parameters. How are they related? They are related by a Majorana polynomial equation. And what do I determine? Give me this symmetric state and give me these parameters Ck. How many are there? At the most, they can be 2n real parameters contained in this Ck. I want to know, do they correspond to a qubit, constituent qubit? Then I have to solve this equation. What is known to me is Ck. What is to be determined is the polynomial z. From the polynomial equation, I have to find what is z. So this z gives me what is beta and what is alpha of the qubits. So given Ck, I can determine the orientation of the qubits. So that is the relation between Majorana representation with the n qubit spin J state. So once I do it, I am assured from by mathematicians say that a polynomial equation of order, say, n, has n roots in principle. There may be distinct roots, there may be not distinct roots, but there are roots for a polynomial equation. If we take all n roots of the Majorana polynomial, they determine the orientation or the points on the Bloch sphere. Now, Majorana stellar constellation is nothing but once you determine alpha L, beta L of your pure spin J state, then you do know that it can be represented as a n-qubit permutation symmetric state. A n-qubit permutation symmetric is represented as stars, constellation of alpha L, beta L on the Bloch sphere. So this is one more picture. So if you want to check how do I look like, in our paper, we have just given what is the polynomial equation, what are the solutions, what is epsilon 1, epsilon 2 for specific cases, what is a GHZ state, and how do we represent it. So this is a typical picture where you do see 3 stars here, and it 0 and 1 are North Pole, South Pole, but this is a point on the Bloch sphere. It corresponds to a specific spinor. So this is a 3-qubit state which has 3 distinct spinors, and you do have a geometry. And if you have any dynamics in terms of a Hamiltonian interaction, you can find how these points evolve. On the unitary dynamics will lead you to a Bloch sphere picture where it will change its point on the Bloch sphere. So this is about it. And when I come to what are all the n solutions of the Majorana polynomials, or let us say they are all identically equal. I may get all z, whatever, z1, z2, zn should be there, but z1 is equal to z2, etc. Then my state is a tensor product of all n spinors. There is no permutation needed for this. This is a separable state. So we do get information about entanglement in a pure symmetric state by looking at the Majorana geometrical representation. If all the states overlap or single point repeated n times on the Bloch sphere, that is a separable state. But if you find any 2 distinct spinors also, it is going to be an entangled state. What kind of an entangled state and its classifications can be studied. So symmetric states with two distinct solutions means I have epsilon 1 and epsilon 2, which are my qubit states. And then I have n minus k times epsilon 1 and k times epsilon 2. And then I permute it. If I take k to be n minus 1, let us say I get a w state, etc. So we can notice that all our decay states, that is Jm, m is equal to minus j to plus j, they belong to this two distinct spinor class, and I cannot make a change from one such state to another if the number of distinct spinors are arranged in different ways. So all these solutions are going to be inequivalent. That is, under stochastic local operations, you cannot reach one state to another. They are geometrically distinct. That's what is this representation tells you. It also talks about entanglement and geometric measure of entanglement and such things. So I move on to the last third part, which is going to be tricky. That involves a geometric visualization of two qubit density matrices. When I move from a single qubit to n qubit pure symmetric states, I had number of parameters increased, but there was a neat correspondence between the points on the Bloch sphere. Fine. But now, if I take any arbitrary two qubit state, not necessarily pure, so what is going to happen to the geometry? That is, can you a convincing geometry where a quantum state is giving you can be written in terms of a geometric picture. So how do I look at it? So what is known to us is geometric picturization of two qubit system has been provided by quantum steering ellipsoid in 2014. Earlier discussions were there, but this kind of a purification, it gives you a density matrix mapped onto a ellipsoid inside the Bloch sphere. So this is what was done. What is a steering ellipsoid? So if you take set of all, you have a two qubit state and you do measurements on one of the qubits, the result set of all Bloch vectors to which one of the qubits could be steered when other party does all possible measurements. It can be analyzed and you will see that set of all such points form an ellipsoid and that lies within the Bloch sphere. So this is what is, that is realization, and such set of points will give you, you can reconstruct your two qubit density matrix if you know the steering ellipsoid. There is a correspondence between a steering ellipsoid and a two qubit density matrix that you started with. So that gives you a geometric picture. So now steering ellipsoid picture, this is helpful in understanding various correlation properties, monogamy and entanglement, quantum discard. It has been used, and these are some of the very interesting references on steering ellipsoid. But what we wanted to do was to take what is the difference in this picture. Quantum steering ellipsoid is the set of all Bloch vectors of the first qubit steered by local operations on only the second qubit. But if you take a two qubit state and you do local operations on both the qubits, is there a specific canonical form that you get? Because local operations are allowed for me, I will try to use local operations and get some geometric structures. Can it be related to steering ellipsoid? Yes, I will be able to relate it, but I may end up with a better, elegant picture. That's what we tried to employ, and it was already known, but no clear structure. That is, given such mathematics, you wouldn't be able to formulate one-to-one correspondence between two qubit density matrix and the spheroid SLOCC ellipsoid pictures. So that's what I'm going to say. All of us know when I take a two qubit density matrix, I do a local operation. A local operation is kind of, if I do a rotation, it's like changing orthogonal basis XYZ coordinate system XYZ to another XYZ. But what is a stochastic local operation that is mathematically represented? It is a 2x2 invertible matrix. We can, for all our purposes, we can choose a determinant 1 because it's invertible. I can take off that factor. So I have A and B, which correspond to stochastic local operations and classical communications, is given by a 2x2 complex matrix. And it is something, to my understanding, it is like a linearly independent basis, not a orthogonal XYZ coordinate system. When I do this, I will have a probabilistic feature here, that is, this occurs with a probability which is in the denominator. Fine, we are bothered about it undergoes a transformation, and I do have a specific mathematical structure of the 2-qubit density matrix. So when I do that, I do notice that SLOCC is a SL2C matrix. Then there is a correspondence we recognize. There is a homomorphism between 2x2 complex matrices and 3+1 dimensional orthogonal matrices, that is Lorentz transformations. So that's a group theoretical connection. So then I will say, corresponding to a plus or minus A, that is belonging to SL2C, there is a 4x4 real matrix belonging to SO31, and corresponding to plus or minus B, I have a 4x4 Lorentz transformation. So I will say now that if I have such a structure, when a density matrix undergoes SLOCC transformation, what happens to Pauli basis? So the Pauli basis under this transformation, it is interestingly, it will only give you a sigma alpha, sigma beta, but it is a LA alpha mu, LB beta mu, that those are the factors that appear in a sigma mu prime under local operations. So this will lead us to the identification that the real matrix, which is associated with a 2-qubit density matrix, this will transform like a LA 4x4 Lorentz transformation, lambda, and LB transpose. What is A? A is a SLOCC on qubit A, and B is a SLOCC on qubit B, and lambda matrix transforms in this particular structure. So then I will notice that under such a stochastic local operation, I do get a valid, physically valid real parameterization of 2-qubit density matrix. Now, instead of a 2-qubit density matrix, if I focus on the lambda matrix, do I identify a canonical form achievable with the help of only the set of all Lorentz transformations? I pick a particular transformation so that I get some simplest form for the lambda matrix. That is the kind of canonical structure that I look at, and then I can identify what is the 2-qubit density matrix. How does it look like when you have a canonical form? This is achievable on the what is called as SLOCC orbit of the density. So now if I take what is called as a Lorentz transformations, which is also called as orthochronous proper Lorentz group. So we have a canonical structure like this. This is also called as Lorentz singular value decomposition, which was first mentioned in 2001 by Verstraete et al. But this work did not give a clear calculation. Can I calculate the Lorentz canonical form? That was not available at hand. So one would make use of their representation and go ahead, but one wouldn't be able to analytically calculate such a structure. So now what we try to do is, let us take lambda and construct a symmetric matrix, that is lambda G lambda transpose, where G is a metric of the Minkowski space. That is, I am talking about a metric in a 3+1 dimensional Minkowski space. And I do know that L transpose GL, L transpose GL is equal to G is the defining property of our Lorentz transformations. I construct a symmetric matrix omega, and notice that this omega plays an important role in analyzing our canonical structure of 2-qubit density matrix. So once I take it, I do notice that the matrix G omega, it has the following properties. That is, this is a theorem. I only want to say that a 2-qubit state has this kind of a rich structure. It wouldn't have been noticed. What we find is omega is a symmetric matrix, but I take a G omega, such a 4x4 matrix. always has non-negative eigenvalues. All the eigenvalues of G omega associated with a 2-qubit density matrix are always positive. And then the eigenvector associated with highest eigenvalue of the matrix G omega, it has either this form, that is what we call as a time-like vector in relativity language, that is highest eigenvalue of the G omega matrix is positive, that is in a Minkowski space. In a Minkowski space, we can also have negative, zero, all such things are possible. But such a G omega, it is X transpose Gx is equal to 0 when we consider what is called as a another form. There are only two things possible. I never get physically valid 2-qubit density matrix will never give me eigenvalues, eigenstates of G omega with X transpose Gx less than 0. You will never find it. You pick all random states and find the eigenvalues of G omega and eigens of them. You will never get highest eigenvalue X transpose Gx negative. It is not possible. So that is the theorem. And then what we do is the condition that I have X transpose Gx is equal to 0, it implies that if I have X transpose Gx is equal to 0, I picked one of the conditions here. That condition leads to only two eigenvalues. Whenever I find X transpose Gx is equal to 0, not all four eigenvalues are distinct. G omega. These are the structures that we notice. It is analytically very interesting. So there is only two, lambda naught and lambda 1. They obey the equation. Highest eigenvalue is lambda naught, and they are doubly degenerate. That is, I get two lambda naughts and two lambda 1s as the eigenvalues of G omega. And in other case, that is X transpose Gx is positive, we do find that the matrix omega, LA omega LA transpose is diagonal. That is what I am trying to say is the matrix gets diagonal form when I have the highest eigenvector of omega G omega matrix, it is positive. And then I do obtain what is the corresponding to 4x4 real matrix. That is whatever we have as a 4x4 real matrix, it has got cut here. So unfortunately, so I will not go into specific details here, but I will only say the corresponding density matrix canonical form is nothing but a bell diagonal form. And in the bell diagonal form, you notice that sigma 1 cross the tensor product sigma 1 and sigma 2 tensor product sigma 2 are given by root of lambda 1 by lambda naught, lambda 2 by lambda naught. They are eigenvalues of the G omega matrix, and lambda 3 by lambda naught comes here. So this is plus or minus is related with the determinant, which is very much important when we try to analyze this kind of structures. But right now what I am telling you is you have to analyze what are the eigenvalue, eigenvector structure of the G omega matrix of a 2-qubit density matrix. Once you do that, I also find what is the other case, that is when you have X transpose Gx is equal to 0. This gives you a bell diagonal density matrix. What does this give you as a canonical form? So if you take that, that is little complicated. I don't get a diagonal form for the omega matrix under such a transformation. And I will simplify it to obtain what is my lambda matrix. Canonical form of 4x4 real matrix has this particular structure where I can find A1 and A0 in terms of the eigenvalues of G omega matrix. So let us suppose that we know to do it. Then I will write what is A0, A1, it is written here. So I will find that this is the structure. It is not like bell diagonal state, it's up diagonal also, canonical form. So once I find this, I can get a geometry. It reveals a geometry for 2-qubit states in terms of the canonical form. How am I going to analyze it? This is another bit which will bring me to the end. So what I'm trying to say here is, if I take set of all projective valued measurements. That is, I take all projectors first. So projectors are 2x2 matrices. When you expand it in terms of the power basis, I have the property because the projectors are positive, I do get the property that E naught, that is coefficient of sigma naught, is 1. And all the other three parameters, even E2, E3, components of this E, they satisfy, that is a unit vector. That is for all projectors, this is 1. Now I go to a local projective measurement on rho AB. I am doing, Bob is doing a measurement E here. That's a stochastic local operation. Once I do it, what am I going to get? I get a probability which is given, I can find out. And what do the steered vectors represent? They lie within the Bloch sphere, because physically speaking, I should get a density matrix which makes me go into the Bloch sphere. That is, points which are steered after Bob's measurement are points within the Bloch sphere. They are ellipsoid. So now, if I take, let us suppose that I have done a canonical transformation, SLOCC transformation, where my state is Lorentz canonical form lambda IC, that is first form, canonical form, where omega is diagonal, density matrix is well diagonal. Then I do have the points, that is steered Bloch points, are given by this kind of structure, lambda 1 by lambda naught. Now, I notice that this steered Bloch points, they obey if I multiply P1 by a lambda naught by lambda 1 and square it, P1 square, and multiply by lambda naught by divided by lambda 1, and here lambda naught divided by lambda 2. I have made a mistake here again, and lambda 3 here. This would obey equation is equal to 1, or set of all Bloch points of Alice's qubit when Bob does a measurement is a ellipsoid here. So, and what is an ellipsoid? It has a semi-major axis. So, in other words, three major axes. They are given by lambda 1 by lambda naught, lambda 2 by lambda naught, and lambda 3 by lambda naught. So this is at the origin of the Bloch sphere. So corresponding to a 2-qubit density matrix, if its lambda matrix is in a corresponding type 1 kind of a canonical form, I do get a ellipsoid centered at the Bloch sphere. So it is a set of all 2-qubit density matrices have for the bell diagonal state are ellipsoids with center as the Bloch sphere. So now, if I take second Lorentz canonical form, that is a density matrix is not diagonal, it has a off diagonal form. So if you take such a case, then I do get ellipsoids. Again, I get similar structure. That is, I collect all these steered vectors of Alice after Bob does a projective valued measurement. I notice that it forms a spheroid, that is A1. There is two A1s appearing. These are the semi-axis lengths. So I do find that it is centered at a different structure. So I do notice that 2-qubit state results in two different canonical forms when I do SLOCC transformations. Allowed pictures for me, one is centered at the origin, and I have a ellipsoid here. Origin has a center. So now I have to verify that all these conditions are satisfied, and if it lies within the Bloch sphere, and then I have a corresponding density matrix which is physically valid. Similarly, if I take a second canonical form, I do find that the semi-axis lengths, let us say 2, are same. It's a spheroid which is shifted. So we do have such pictures, spheroid inscribed inside the Bloch sphere, correspond to the collection of all Bloch vectors. That is, I have been repeating because mathematics may go away, but it's a calculable, analytically realizable kind of structure, which is very important. So with this, I have reached the end of the story now. So we talked about what is Majorana stellar representation for pure symmetric N-qubit states, and SLOCC canonical forms and associated ellipsoids and spheroids, only two structures here. So they are inside the Bloch sphere. Now, we have also worked out how to calculate, let us say, concurrence. How is the volume of these spheroids related to monogamy and other aspects. And they are found in our latest paper, where we have only restricted ourselves to pure symmetric n-qubit states and picked 2-qubit reduced density matrices. They give a very nice structure, and it will reflect in with these kind of pictures. That is, n is equal to 20, 30, kind of all kinds of pictures for different n-qubit symmetric, pure symmetric states when I draw reduced systems, and it is analytically very interesting to see. Thank you for your attention. Maybe I have ended my talk early, so I would like to have some questions if you have any.
Thank you, Professor Ushadevi, for a wonderfully delivered and detailed talk. It is appreciated very much.
Thank you.
And the floor is now open for questions. I request the audience to please raise their hands so that we can go in a chronological manner. Audience? Organizers, if there are questions from the YouTube channel, could you please forward them? Okay, we have one question from Lavakumar. Lavakumar, can you please unmute yourself and ask?
Okay.
Ma'am, can we generalize your that's like for 2-qubit you are showing this Bloch sphere representation and all, right?
Yes.
Can you do it for 3, 4?
So that is a ambitious thing. But generally, what is told is there is a one-to-one kind of no doubts about it, kind of a representation, which reveals itself in nice structures. There are discussions on higher dimensional, say, for example, even in 2-qubit states, there are SU2, SU4 kind of a picture, which is not very clear. Mathematically, it gets complicated, but it is good to have such pictures because it reveals in a different way. I would say it is like in a harmonic oscillator, if we do a differential equation or a creation annihilation operator picture, it gives you different. So we should have such insights, geometric insights is what I believe. But trying it, say for example, Majorana stellar representation gives you only for pure n-qubit symmetric states.
Yes.
And we only know about 2-qubit structures, geometric structures. I don't know any other clear pictures for other quantum states, geometry.
Okay. Thanks.
Thank you.
Yeah. Usha, I have a question.
Yeah, please.
Yeah. Symmetric state means bosons, right?
Yes, if you take it as both, yes, fine, agree.
So that means we don't have any insight about fermions, totally antisymmetric.
No.
I see. Okay.
So that is geometry. As far as geometry is concerned, that is, I have to relate the parameters of one to another in a neat way.
Okay.
So that I don't know.
Yeah, this itself, 2-qubit itself is highly non-trivial. That is true.
Very non-trivial.
Yeah.
But, yeah.
Thank you. Yeah.
Thank you.
Okay, the audience may kindly ask more questions. We have some time.
I also want to tell the chair for this session. So you said you are a biophysicist, so I just wanted to say that these Mueller matrices which can be analyzed for, say, for example, I have a RBC or some tissues which I have to analyze using a Mueller matrix parameterization and things. And mathematics that what I have represented for 2-qubit density matrix, it is applicable to even for Mueller matrices of optics, basically. That is to say, people have analyzed what is a 4x4 tomography of the medium. Say RBC can be represented as a 4x4 polarization medium. Then also, this particular formalism gives you how physical it is and what kind of information can be drawn by this kind of geometric pictures, basically. Just wanted to say that out of context.
Yeah, that's a very nice perspective. If I can ask pretty much an extremely naive question coming from where you asked. So, in biological physics, things are extremely dynamic. Okay, so we have these states, metastable states, and we have frequent state conversions.
Yeah.
I was wondering if we could also associate dynamics with these, look at how these things change over time and perhaps gauge some kind of a decorrelation or something. I don't know.
Yes,
It's
it is possible. I have only presented a static kinematic structure. But if you take a specific Hamiltonian and analyze it, say, or in other case, you have a time development of these parameters. It looks like an interesting picture of the parameters that you do have, such, how they can vary and what prevents them to go beyond this or such limits and all that.
Okay.
It is being done. Yes.
Professor Ushadevi, we definitely need a lot of crosstalk in today's day and age between different kinds of scientists.
Yes.
That would be a privilege, actually. Thank you.
Ma'am, I have one more question.
Yes, please go ahead.
Please.
Ma'am, suppose if this, if we look at the, if I want to see the dynamics of this 2-qubit system in a dissipative environment, say, suppose, observe the coherent evolution.
Sure.
So this ellipsoid will be like shrink or it changes the shape
Yes, that's what. That is, you do have, if you check Nielsen and Chong, he will give you for amplitude damping what is the picture in the Bloch sphere. But this is a different picture. That picture is with some different parameterization. But this actually, that is from a single qubit dynamics is given in Nielsen and Chong picture. What happens to a single qubit dynamics under, say, amplitude damping? So, but now if you want to check what is a 2-qubit dynamics, you would have to take these kind of ellipsoids and spheroids and then see how it shrinks, how it expands under a particular dissipation. That can be done. Yes.
Okay. Thanks.
Okay. More questions from the audience? We do have a couple of minutes left. Okay. If not, Professor Ushadevi, thank you very much for a very wonderful talk. And I thank the organizers, particularly Professor Prashant Panigrahi, for inviting me to chair the session. I learned a lot. These both talks were extremely interesting. And for somebody who's completely out of the field, it's good to listen to these pedagogical talks. So thank you very much.
Thank you.
Thank you, Professor Panigrahi. I will hand it over to the organizers now.
Thank you all for being, for attending the conference. This is the end of today's session, and tomorrow's session is going to start from 10 a.m. So please tune in, and thank you all.
Okay, so thank you. See you tomorrow.
Yeah, thank you, sir.